Hi everyone, my name is Peñayorra, and today I'm going to be presenting you my work on intelligent navigation and control systems for manned celestial body descent and ascent. The objectives of my PhD are to investigate and innovate adaptive systems for autonomous landing in harsh environments, accounting for high-fidelity environment and system models, and trying to increase the system resilience against unexpected events and uncertainties. Last year, I presented this graph with the key concepts I wanted to explore, where I concluded that the HCA systems were the focus of my PhD research. HCA stands for Hazard Detection and Avoidance Systems, and this is what I will be talking about today. So at that time, we planned a methodology and a roadmap. The first thing was to create a baseline GNC simulator, which we called AstroSim, and then implement the different techniques for the key concepts I just showed you before. One of which was this hazard detection and avoidance systems, which I now collected into this module called Astro HDA, which belongs to AstroSim. To assess the performances, we wanted to perform some analysis. With that, maybe get some publications and use those analyses to consolidate an algorithm that would conform the final version of this Astro HDA. And then finally, take the algorithm through a testing process to raise the technology readiness level. And this is what I'm currently doing at my secondment at the FKI Bremen. Today, I will be talking about Astro HDA and about the secondment I'm currently taking part of. So Astro HDA is composed of 3 layers for hazard detection, namely shadow detection, feature detection, and slope estimation. And it's a passive system, meaning that relies only on images. For example, active systems typically include LiDARs, for example, which are systems that emit a signal and then receive it. So they are actively learning about the environment. This is the difference between passive and active systems. And the key features of Astro HDA is that we want a system that's able to generalize and evaluate from single instance image acquisition. This is better to adapt to unknown conditions and also to extract information from little data. The layers that we use for the hazard detection are based on image processing techniques, based on convolutional neural networks. The results I'm showing you today are using the ResNet34 as backbone, and the technique I'm using is semantic segmentation. The first thing we need to do is to create a database, and for that, I developed a pipeline based on Blender, which is also, this pipeline is also included in AstroSim, one of the submodules, where we take meshes that in this case belong to asteroids and comets, and we distribute stochastically feature populations so we can enrich the heterogeneity of the generated dataset, right? So we use these images for the training of the set, and the results we obtained are using these images. So on the left-hand side, you can see what I call the naked mesh, where you only have the mesh of the body you're looking at. From that, we need to first extract the slope mask, which is what you see here, which is currently based on thresholds. So slopes over 15 degrees are considered dangerous and therefore red. And the slopes under 15 are considered safe. This is the ones you see in green in this image. And also for the feature distribution, you can see 2 examples of the same image from the same camera position with the same illumination conditions, but with 2 different feature populations, which are stochastically distributed, as I mentioned before. So the first layer is the shadow detection. Shadow detection presents really good results. And the top losses that we see on the right-hand side are or belong to the images where very dark images where we can barely see the asteroid. The loss value comes predominantly from the limb estimation and not so much from the shadow estimation, which is actually pretty on point, as you can see. For feature detection, we also obtained very good results. You can see on the left-hand side that the prediction actually take usually more natural forms than the original rectangles that were imposed for the mask creation or the labeling, if you prefer to call it so. And in the top losses, we see images that, again, are in very bad illumination conditions and for which most of the cost comes from the limb estimation, not so much from the feature detection. Slope estimation is the most difficult layer of the three of them, and this is why typically LiDAR systems are used. And as we can see in the predictions, areas that are shadowed are not so well predicted, but when the illumination conditions allow for it, the prediction is able to estimate properly the threshold that we imposed for the labeling. We can also see how actually the prediction takes more natural shapes and does not really pay attention to the very small red dots that we can see on the target on the, for example, left bottom plot. We still need to understand whether this is something we want or not, because it's always to be on the safe side and label something as dangerous rather than safe and then being wrong. And then again, the top losses, we see images which are very dark, and an image, which is a particular case, which is actually the worst estimation according to the criteria we have chosen now. But upon visual evaluation, at least me personally, I think the estimation is not that bad. And the problem is that it's staying on the safe side of it. And I think this is something we need to think about this criteria, because in my opinion, this estimation is not one of the worst ones, even if it's predicted as such. So we need to work on the accuracy criteria and the loss criteria as well. Then with these three layers, we are able to superimpose them and conform what you see on the right-hand side, which is a safety map that tells you the areas where it's safe to land in green and the areas where you should not land in red. We also wanted to test our algorithm with images or with bodies that have not been used for the training set. So we composed a test set, a smaller one, with 4 different bodies using different feature distributions as well. And we tested our layers again. Shadows were estimating the target with a very high level of accuracy, as you can see in this image, for example. Same was happening for features. But we found that for slopes, it's important to have bodies that resemble at least the bodies you're going to be evaluating your algorithms on, because they not so much learn the slope from the image, but they learn the bodies that you include there, is what it seems. So this is, of course, not ideal from a generalization point of view, but having access to a rough estimation of the body's morphology is something that you typically have much earlier in mission stages. So that's something that we could ideally include in the training, because it would be interesting, and this is something that we are currently researching on, to include rough estimations of the surface of the geometry of the body as labels, and see if this can actually improve the results when it comes to generalization. Of course, it's not generalized because you have to use the body that you're going to be evaluating on. And then, yeah, this is part of the work we need to develop. I have to say that this was not the case for all of the images, but it was relatively or frequent enough that it raised an alert, and this is why I'm presenting you these results, which is this one is not one of the best ones we've obtained with the tests, but I think this is what we have to show here, the parts where the algorithm actually fails. Currently, I'm doing my secondment at DFKI Bremen. Well, I did my first one at Politecnico de Milano last year. Here, I'm working on a one-leg hopper that you can see in the picture. And what we want to do is include a perception layer to feed the controller with information obtained with the maps I just showed you before. This robot moves in only one axis, so we want to find a safe spot for its foot to be placed. If this is successful, then we will later expand to 2 dimensions. What we want to do is include sensors in the loop, which first of all is a Raspberry Pi camera module that will allow us to take real-world images and feed that to the processing unit. And then if this succeeds, we want to include processor in the loop, which would mean running AstroHarm in the Raspberry Pi 4. This would enable delivering processed input directly instead of raw sensor acquisitions. What I'm showing you here are some images I took with my smartphone that I wanted to test for the layers I showed you before. I 3D printed some features, and then I took these images, and these are the results for the shadow detection. I'm not showing you the target here because we don't have it, but I'm showing you instead the probability map, which is something that I can also obtain with my neural networks. You can see that shadows are very well estimated, even for real images, and in illumination conditions which are different from what we would expect in an asteroidal environment. Features, on the other hand, are completely lost, and not even the probability map shows any sign of proper estimation. We can see how the limbs of the crater are somehow detected, but nothing that resembles what we are actually looking at. So we need to work on this and understand why this is not working properly. Again, illumination conditions might be playing a role here, because here we have light diffusion, and this is something we need to take into account. And then the slopes actually output a reasonably good estimation of the mask, even though it looks more like a feature detection than a slope prediction. And we can see as how the probability map is much more foggy. It's not so binary anymore. And this is something I would really like to work on as well, because we can get much better prediction layers if we play with this probability and we post-process it a bit. The idea here is, as we have a one-dimensional leg that can place its foot along the blue line you see on the central image, we then want to post-process this safety map to the one you see on the right-hand side, which is a simplified version, and then find the largest spot where the foot can be placed, and that's where we should order the controller to try to place the foot, right? So some improvements to be done. We want to improve the overlaying for safety map creation using these probability maps. We want to improve the loss estimation criteria to make it more sensible. And then the dataset, we want to use preliminary shape models of the target for slope estimation, which was the part that was failing in testing, and include more surface saturated images. And then now we're working on increasing the TRL of the already obtained algorithms, including sensors and processors in the loop. Talking about publishing, last year we had these 4 objectives. Publishing Astrosyn was the first of them, and we managed to do that at SciTech 2022. We also wanted to publish Astrohan, which was a collaborative work with University of Iași, Romania, and we also managed to publish that in Proceedings for International Astronomical Union. And we wanted to publish landing simulations, which was the result of my contribution to Politecnico di Milano last year. We are currently under a review cycle for advances in space research for a journal paper, but it's under a major review, so chances are we're not gonna go through it, but we'll see. We did our best. And then about HDA, Astro HDA, we have been accepted at the ISSFD this year for China. It's only a conference paper, but it's a beginning, and I will be pushing forward to try to publish this now in a journal, since we are getting close to the end of my PhD and I need this publication. For training, we had 2 workshops. Well, actually, it was 1 workshop and 1 training school, both online. And then for outreach, we were not able to do that much because COVID happened. But there's an Instagram profile that some people at Stardust have opened and are managing, and I would really recommend it. Also, as the last point, we had this Andrea Milani competition challenge, which we took part of, was organized by ESA, by the Advanced Concept team, and also by Stardust. We won the student competition. We were the best student teams, and we were 3rd overall, when including also the professional teams that usually take part in these kind of competitions. So pretty happy with the results. I'm very happy with the people we managed to select. It was a tough process. It was not only technical, but also like managing all these different students. And it was a nice thing to do as well. These are some of the references I used for this presentation, and thank you very much. I hope you enjoyed it.